right, let's see. Is it time to get started? Some weird background noise. Maybe it's going to clear itself up here in a little bit. All right, let's see. Is it time to get started? Oh, that was me. All right, I'm going to go ahead and get started then. Today I'm going to tell you about how we've been leveraging machine learning to accelerate simulations of dilute alloy catalysts with adsorbates. And if you followed the last couple of videos on the papers, it gave some walkthroughs of 3 papers around a machine learning potential architecture that we created, with another one on how we accelerate geometry optimizations, and then putting it together to look at adsorbates. So today I'm going to take some time and go through in more detail in a format that is designed to explain a little bit better in this format than just walking through the papers. So let's get started. So I'm going to focus today on single atom alloys, and I'm going to take a minute to say why those are different than regular alloys. So regular alloys, I think, is traded. That is, metal A and metal B are surrounded by each other, and they interact with both A and B. And in the single atom alloy limit, we go to the very dilute limit, where we have, for example, lots of gold atoms over here that are relatively inert, with just a few of these red atoms that might be palladium or platinum or something that's very active. So the noble metals here, they have completely occupied d orbitals, and the active metals don't. And that makes them very different than something like nickel platinum, where both metals have unoccupied d orbitals. And in our past work, we've shown very standard ways that these orbitals mix and how they work together to modify alloy electronic structure. In single atom alloys, because one metal is full and one metal is not, they can't mix the same way, and I'll show you in the next slide that it leads to a totally different electronic structure, which is one of the reasons why we're interested. And so what we started this work out in is thinking about selective hydrogenation of something like acrolein on a dilute palladium-silver alloy. So acrolein is shown over here. It has a carbon-carbon double bond and a carbon-oxygen double bond. And you would like to be able to selectively hydrogenate one over the other, and not both of them. And so that's what got us started, and to think about how we would simulate and model that and determine if a single atom alloy is going to be suitable. So I won't tell you the end of that story in this talk. It was a long path to get to where we are. So why are the single atom alloys different? One way to think about it is the red atom here is surrounded by noble metals that it can't really interact with. And I'm showing that in this figure over here. These are electronic densities of states, where the green bar or curve here is the density of states of this red atom. And what I want to point out is this is palladium, iridium, rhodium, nickel. These are the single atoms in these hosts copper, silver, and gold. And what you see is these very sharp green peaks. Now, in a regular transition metal alloy, these would be spread out and broad because of the coupling between the transition metal d orbitals. But what you see in these cases is the sharp green feature does not hybridize with this red band from the noble metal very well. And these sharp features make it look like you have a gas phase metal atom that's embedded in a sea of electrons. And that's what's interesting about them. They don't follow the normal d-band model. And because these act like electronically isolated atoms, they have different reactivity, and that can lead to interesting properties. Now, once you start getting palladium-palladium bonds or metal, any of these where they form dimers and trimers, now they couple with each other and they broaden back out to regular transition metals. So the key for single atom alloys is how do you get a single atom, and we need a lot of them for it to be active, but we can't have too many, or you start forming dimers and trimers and other kinds of things. And so that's the kind of thing we were interested in asking. How do we design a single atom alloy catalyst where we need to be in the single atom alloy limit, but we want to have a lot of single atoms. So those are the real challenges. How do we find a bulk composition that does that? And this is hard because the surface composition is never the same as the bulk because of segregation. And once you have adsorbates and reactive environments, then you can have those adsorbates interact with those metals as well. So that's a problem of just how do we account for these two things in here. So the second challenge is it's in the dilute limit, right? So this is kind of a schematic of what a dilute limit looks like, and this is way too big of a system to think about modeling with DFT. There's too many atoms, too many electrons, and even if you could do one, it would be very expensive, and we need to do way more than one because of all the different ways you can arrange molecules on the surface. And so that's a problem. We can't use DFT directly. And the other problem is acrolein is a kind of, quote, big molecule, big for people that do surface DFT calculations. And that means that, you know, there's lots of ways that you can put it down on the surface. There are a couple of different configurations here. There are lots of ways the bonds can break. And all of those mean we need a lot of calculations. And because there are so many ways for the molecules to move, these relaxations are going to turn out to be expensive. All right, so the goals in our work that I'm going to show you today were to really figure out what surface composition of a dilute silver palladium alloy in the presence of acrolein as a function of bulk composition. So how do we say what that is likely to be? And the basic method is builds on work I did in my postdoc with Carsten Reuter that we talked about in this paper, which is we have to know segregation energies, we have to know adsorption energies, and then what we do since this 2008 work is that we combine it with Monte Carlo sampling. And the challenge here is in 2008 we did this for a small unit cell that was fixed at silver 3 palladium because we did it all by DFT. So every one of these lines was a set of DFT calculations. And now we combine this with machine learning to build surrogate models for each part of this. So that's going to allow us now to look at continuous bulk composition in the dilute limit, and we will be able to consider at least hundreds of adsorbate configurations. But otherwise, things are basically the same. We still have this kind of formalism where we can think about the surface energy of a configuration. We account for chemical potential of the alloy so that we can change the composition, and we account for a adsorbate reservoir to exchange with as well. All right, so here's the schematic. What we would like to do is a big simulation like this where we can move or exchange atoms, and we can calculate the change in energy. We can put adsorbates on, calculate that change in energy, and then if the change is favorable, we accept it, and if it's not, then we reject it. And that is your basic Monte Carlo algorithm. The couple of things that don't work, again, we can't do DFT on this huge thing here. And what we do instead is use molecular simulation and machine learning to do it. So what we did before in some previous work was use a very big slab, say 10 by 10 by 15 layers. And that's enough atoms, 1,500 atoms, that you can fix the composition and just let segregation do its thing, and it doesn't change the layers concentrations in the middle too much. But in the dilute limit, that doesn't work because there are so few atoms that it doesn't help you. And it was also expensive because it was such a big slab, even with Monte Carlo. So what we wanted was to use smaller slabs like this, and the challenge then is that we need to couple it with a chemical potential reservoir and do something like semi-grand canonical Monte Carlo. And so that means we need to be able to map this chemical potential to a bulk composition so that in the end we know what we're in equilibrium with. So I'll show you how we do that. We will then have a way of calculating this chemical potential, this slab energy, and the last thing we need is the adsorbate energy. And we'll get to that in a couple of slides. And after we have all that, the great thing about this approach is we can do these Monte Carlo simulations in Python, and they're not that hard to write. All right, so let's talk bit about the semi-grand canonical Monte Carlo idea. What we do is have a fairly thin, small slab here that's going to exchange atoms with a bulk reservoir. And so we can take a gold atom out or a silver atom here and put it into the reservoir, and then take a palladium out and put it in, or vice versa. And the change in energy is associated with this delta mu. So all we have to do is decide what delta mu we want, and we can do this simulation, and then to relate it to something that's relevant, we have to relate the delta mu to a bulk composition. So we do that. We do energy as a function of steps. Eventually it stabilizes, and the compositions here stabilize, and then we know what is the slab composition that is in equilibrium with that bulk reservoir. So we did this calculation with our single neural network, and we were able to estimate the bulk alloy chemical potential. So to do that, we first need a way to calculate what the change in energy of a bulk system is. So we make a whole lot of different bulk configurations. We train a single neural network on it. These figures here are kind of simple parity plots to show that what DFT says the atomization energy is the same as our neural network potential. And that means for any given bulk configuration, we can accurately calculate the total energy. And then we can do Monte Carlo in equilibrium with a delta chemical potential. And that gives us this kind of information here, where you specify a chemical potential that you want to be in equilibrium with. We run Monte Carlo until the bulk stabilizes, and then we can come up here and map it over to what the bulk concentration that corresponds to that chemical potential is. And you can see here we have this essentially linear relationship in what we consider the dilute limit. And once you start getting palladium-palladium and silver-silver interactions, it becomes nonlinear, and that's interesting, but not the region we want to be in today. So just to remind you, these results, of course, depend on DFT, and we use the PPE functional and VASP to calculate those things. So the results are kind of consistent with that and limited by that. If those results are wrong, then these results are also going to be wrong. All right, so that gives us then the bulk composition and chemical potential that we need. That allows us to do the same thing with slabs. So now the difference with slabs is there's some vacuum. And we do the same kind of exchange. We have a separate second single neural network for the slab energies. And on the right here is a typical kind of result that we have, where we take a slab, allow it to exchange palladium and silvers until the energy is constant. And once this is constant, we know what it is in terms of the second layer and the first layer. And you can see for this particular composition that started out at, say, 20% palladium, that almost all of it goes into the bulk. There's hardly anything in the surface. And the surface is dominated by silver in that case. And the second layer is enriched in palladium. So the palladiums just move from the first layer to the second layer, and there they are. Okay, so that lets us now map over some chemical potential space. So here we're going for slabs in equilibrium with a bulk from, say, 6% to 32%. And we do the same thing. This is now something in vacuum. And we can see that up to about 15% bulk palladium, we see no palladium in the surface that is really measurable. And that's because it's all going into the second layer. And the second layer is quite rich in palladium, much richer than this bulk composition as a result. So this is not super different than what we observed in 2008, other than we now map this across the entire composition space by this coupling to the bulk concentration and the use of the semi-grand canonical Monte Carlo. So what does this mean? Everybody, I think, in experimental surface science knows that silver segregates, but it's a little less commonly known maybe that you get the second layer enrichment, and that means that there's potential for adsorbate-induced segregation. And in fact, the palladium in the second layer doesn't really have that far to go. It just has to swap with the silver layer for it to enrich the surface. So how do we talk about the effect of adsorbates? This one was complicated. It starts with DFT. So the first thing we did was, look at these 16 prototypes and looked at, pure silver. These ones have 1 palladium. These ones have 2 palladiums. Some are 3 palladiums, and this one has 4 palladiums. We looked at all of these by DFT, and let me walk through what this figure on the right is. The first thing we calculate in red is what is the segregation energy. So the red curve is all positive, which shows you that to take palladium from the bulk to the surface is uphill in energy in every case. And that's why we see silver segregation to the surface. Then we calculate the adsorption energy, and on all of these, the adsorption energy is always negative, but it's not really negative, and it's not negative enough that when we combine it with the segregation energy, we only see one configuration that is a little bit favorable in terms of energy. Now, this is a little bit misleading. This is only 16 configurations, but 15 of them are unfavorable, and that gives you an idea of why it's important to be able to sample hundreds or thousands of configurations to make sure we find the ones that are reasonable and that are favorable. And these were pretty expensive to do, so we did not want to go about calculating hundreds or thousands without a plan. So to come up with a plan, we invented a third kind of machine learning model that is going to give us a reasonably accurate adsorption energy for acrolein on some kind of adsorption site. So to build this model, we're going to need a few hundred adsorption energies, and those are going to be relaxed energies, and I indicated earlier that they're not that cheap. So I'm going to show you how we accelerated those so that it became pretty practical. And in the dilute limit, we have a large number of sites, but they're basically discrete. And so we don't want to build a full atomistic potential for this. That's too expensive in terms of training time. And what we want instead is, if we pick a site, can our machine learning model tell us what the most likely stable adsorption energy on that site is, like the minimum of all the possibilities. So we still have to do some enumeration and computing, and that's what we'll do next, I think. So before we get there, we have to be able to map the adsorption energy of a configuration of acrolein on one of these sites. And these are expensive. I'll show you how expensive in a little bit. And so in parallel, we were working on how do we accelerate the geometry optimization to speed it up. And so the idea here is we go back to our single neural network idea and ask, can we incorporate that into the geometry optimization with VASP? And so the idea is, if the single neural network is accurate enough, we do the optimization with the neural network because it's cheap and fast. But if it's not accurate enough, then we switch over to VASP. We get new calculation data. We feed that back into the neural network to retrain it so that it's accurate again. And then we use it for the optimizer. So that's a big advantage over starting from scratch every single time. Most of these geometry optimization algorithms, they're almost all gradient descent, where the gradient is the forces. And they have a way of iteratively learning the Hessian, like in BFGS or some of them. But you start from scratch, the identity matrix in every case. And with this, we're able to optimize many geometries in parallel so that our surrogate model gets better and better as it goes and more accurate. All right, so I'm going to skip a lot of the details and mostly convince you, I hope, that it works. And it works really, really well, especially for complicated geometries. So here we're comparing the neural network active learning approach in the paper to just using VASP quasi-Newton. So for simple, highly symmetric systems like these clean, flat surfaces, even this small step surface, you don't really see a big benefit. These ones are so easy to do, you don't really need to accelerate them. But once you get to like 643 or surfaces with adsorbates, we start to see a factor of 2 or 4 reduction in the number of DFT calls that have to get made. What does that mean? If this was a geometry optimization that used to take 4 days, now it only takes 1 day, or 4 hours and 1 hour, etc. So this is a huge savings if you're able to do it. So we've looked at a bunch of different approaches to doing this. Even the most naive Gaussian process acceleration method results in a huge savings for the acrolein relaxation. So without any acceleration, it takes about 190 DFT steps to relax. With any kind of machine learning approach, we get a huge reduction down to 40 calls. If you use our single neural network and you train each configuration on its own, we get about 18 calls. And if we are doing it in parallel, we can get it down to about 10 or 11 calls. So massive reduction in compute time to get the accelerated geometries and energies which we use in the adsorption. This also works for nudged elastic band calculations. This is a platinum heptamer that is an island on a surface that rearranges from this shape into this shape. And here we have we used EMT for this because this was a quite large calculation. But you can see we go from almost 600 steps with MD-Min to 9 steps with the neural network machine learning approach. And if we look at this, this is a reaction of ethylene or acetylene hydrogenation. And it takes over 1,100 steps out of the box. And with our neural network, we can get that down to 30. So huge savings. We're really excited about the idea of using these surrogate models in conjunction with geometry optimizers to get much faster results that are basically the same accuracy. All right, so back to acrolein. What we did was take our surface and enumerated a subset of configurations that gave us about 540 different potential adsorbates and geometries. And then we used a fingerprinting scheme to eliminate anything that was symmetrically equivalent. So out of the 540, we got that down to 287 unique adsorbates. And they might be related by symmetry, but those will have equal equivalent energies. So we just eliminated them. And then we created a nearest neighbor machine learning method to look up the most stable adsorption energy for any site from its fingerprint. So these red dots here indicate pseudo-atoms, where we use that to identify the site. And then we use the local atomic environment fingerprints to characterize what local environments are there. And those map onto the minimum energies that we calculate by DFT over here. And what you can see in this parity plot is what those look like. So there's a lot of them that are pretty good along here, and pretty good means root mean squared errors are not too bad. The worst one are for the bridge sites, and there's a couple of outliers out here, but for the most part we have RMSEs of about 0.1 EV for this system, and that's good enough, I think, to understand what the impact of adsorption is. So let's put it all together now. We have a machine learning model for the bulk that allows us to calculate the relationship between bulk composition and chemical potential. We have a machine learning model for the slab that allows us to calculate this equilibrium here. And we have a machine learning model for adsorption. And so we can put those two things together, and that allows us to analyze this particular kind of result once it hits the equilibrium limit. So that tells us a couple of important things. One is acrolein absolutely induces segregation very readily at 373 K. So I showed you before, in vacuum, there's hardly any palladium in the surface, but under reaction conditions, basically every molecule at 1/9 of a monolayer anyway is bound to a palladium atom. So as long as there is palladium on the surface, or acrolein on the surface, there will be palladium at the surface. And you can see it's at the this is the 11% range. So this is at 1/9 of a monolayer. And as you increase the bulk concentration, you start to increase the number of palladiums at the surface, which indicates that they are aggregating. I'll show you that in another slide here. So we can count the number of sites and the kinds of sites. So the blue dots here are the single atoms, and so up to about 7% you see we are 100% on top adsorption of acrolein, which means single sites. And around here, you start to see an increase in the orange. So from here to here, we start to see bridge sites forming, and that means we have dimers. And as the dimers form, you also see a few trimers. So within the limitations of like all the DFT approximations we've made, all the energetics and how those propagate through Monte Carlo and how they propagate through the other things that we've talked about, this gives us an idea that we should not exceed about 7% palladium in the bulk if we want to stay in the single atom alloy limit. That is, if you go less than this, you'll have single atoms, but fewer of them. And as you approach this, this is really about the maximum you could expect before you start seeing dimers and trimers and aggregation. That will give you a reduction in the selectivity or properties that you were relying on there being single atoms. All right, so I'll conclude there and say I think we've successfully used machine learning in a couple different ways to extend the reach of DFT so that we could model catalytic systems that aren't really tractable with DFT. And that is these dilute limit alloys with adsorbates and statistical sampling. The conclusions are limited by the DFT parameters, especially the exchange correlation functional. So if, for example, the accuracy of van der Waal interactions is important, then that is likely missing for the most part in what I've described, except through fortuitous cancellation of errors. That also includes the role of relaxations and vibrations. We didn't really include vibrational entropy, for example. We did include configurational entropy via the Monte Carlo, but not other kinds. And that's still pretty challenging to do, and it's a kind of future project for someone. It still turns out to be pretty difficult to compare this with experimental work. The surfaces we modeled it on, they're still 1-1-1 surfaces. There are no steps, there are no particles. We still don't talk about reactions. Those could be added, I think, but would probably need a different approach than what we've done. And it's really limited because it's so difficult to characterize the dilute alloy under reaction conditions. There just aren't very many of those atoms. But I still think it's a pretty big step forward since the work I started on this kind of like in 2008. All right, so I'll end there. Maybe if there are any people that are watching, I guess you can put something in the chat. I'll advertise our @cat Discord server just briefly. This is, if you're not familiar with what Discord is, it's a text, chat, and video channels place for the catalysis community. We started it last fall at the AICHE meeting to give people a way to interact with each other and chat with each other, and it's something I hope we'll continue figuring out how to use. So I think that's it. I'll maybe wait a few minutes and see what happens here. And if there aren't any questions, then I'll just end the stream and you can leave comments on the video later. Thanks, Liz. No worries, Lars. It'll be it's being recorded, I guess, so it'll be visible later if you feel like it. Hey, Hong Liang. All right, I'm not seeing too many questions. I think if anybody has ideas on what else we could do with that cat or this format, I think it should be pretty fun. Yeah, a watch party would be something. All right, I'm going to end the stream then, and feel free to reach out to me or leave a comment on the video afterwards, and hopefully I'll see a lot of you in person. Let's see, in the GCMC there is an acceptance probability of unfavorable geometries, and it's the regular Boltzmann kind. So you calculate the delta E, and if it's negative, it's always accepted, and if it's positive, it's accepted with the right kind of Boltzmann probability. That is essentially how it allows for configurational entropy, and it's temperature dependent how that acceptance rate goes. All right, I'm going to go ahead and end it, and hope I see some of you in person pretty soon.